Hello. Today we will look at an example of the mode system that we studied in the last class. In the last class, we wrote the field expressions for several types of modes like T to X, Tm to X, or Te to Z, Tm to Z, etc. in terms of the vector potentials A and F. Today we'll take a specific example called rectangular waveguide and study the modes of this waveguide. Today we will study T to Z modes. I know you have done this, it's nothing new here, so I'll go reasonably fast, but the only difference is the approach. The approach that we are going to learn today is very generic. As we go along in the next 2 or 3 lectures, you'll figure it out that the system is very generic and you can simply extend it to several types of solutions. So let's consider transverse electric to Z, TE to Z. We always define the coordinate axis to which the fields are transverse to, or which component of the field is transverse to. In this case, it is transverse electric to Z direction. That means Ez is 0. If I were to say TE to X, then EX will be 0, and so on. So what is the process? We want to specify the condition for F and A. What we are trying to hypothesize or we are trying to proposing here is, if you choose F is equal to AZ cap Fz and A is equal to 0, then we get the solutions of del square Fz plus beta square Fz equal to 0. If you find the solution and you find out the field quantities, Ez will become automatically equal to 0. Therefore, we get Te to Z solution if you choose F equal to Az cap Fz and A equal to 0. We had seen this before. And of course, we are going to say that Fz xyz equal to f of x times g of y times h of z. Nothing new in this slide. It is a repetition of what we did in the last class. Now we are going to ask the question, how do we find Fz? If we find Fz, then we can find the electric and magnetic fields. So Fz is a solution of del square Fz plus beta square Fz equal to 0 and plus something more. So the approach that we are going to follow is separation of variables, where Fz is represented as a product of a function of x f of x, function of y g of y, and a function of z h of z. We have done this, substituted this in the equation del square Fz plus beta square Fz equal to 0. And you expand del square in rectangular coordinates as del 2 by del x square plus del 2 by del y square plus del 2 by del z square. And since g and h are not functions of x, it comes out of the first term. Similarly, fh comes out of the second term and fg comes out of the third term, and so on. Divided by fgh, you have sum of an x dependent function plus a y dependent function plus a z dependent function plus a constant equal to 0. Therefore, each of them must be equal to 0. That is, x dependent function plus some beta x square, some constant 0 equal to 0. Similarly, a function of y plus beta y square is 0, and similarly the third quantity. And the separation values beta x square, beta y square plus beta square z square, sum of that will be equal to beta square, which is omega square mu epsilon. We have done this before also. We have seen it before. Another revision. Okay. You also remember that the solution of the second order differential equation d2f by dx square equal to minus beta x square f of x is of the form e to the power of minus j beta xx or j beta x plus j beta xx for traveling wave. If the system is standing wave, we assume the solution to be of the form cosine beta xx or sine beta xx. When you have a system where the fields are going in only one direction to infinity, there is no reflected wave, then we have assumed the solution of the form e to the power of minus j beta xx for a positive x going wave and e to the power of j beta xx for a negative x going wave. Suppose we are trying to find the fields in between two objects, two boundaries which are reflecting in nature, then we assume a standing wave solution of the form cosine beta xx and sine beta xx. Usually we take the linear combination of these two with some unknown coefficients as the final solution. And those coefficients are obtained by satisfying the boundary conditions. Even the value of beta x is also obtained by satisfying the boundary condition. That is the part which we are going to be trying next. For this, the boundary value problem we are going to be solving is a rectangular waveguide. It is a hollow metallic tube, and let me pull out the pointer. This is the metal. It has 4 metal surfaces. It is going to extending to infinity in the z direction. The size of the guide, usually the broad wall is aligned along the x direction, narrow wall is along the y direction. Typically A is greater than B, but it's not necessary. The solution doesn't really assume anything of that kind. So the x dimension is A and y dimension is B. Usually the waveguide is aligned in the coordinate system such that one of the corners sits at the origin. This is not necessary. There are solutions where this could be, the origin could be right at the middle of the guide. Then the waveguide extents will be minus a by 2 to plus a by 2. In the y direction, it extends from minus b by 2 to b by 2. The solution form will be slightly different, so we just have to pay attention to that. That's all. These are perfect electric conductors. That means the boundary condition on these will be tangential E is 0. Right. So in the x direction, we have a choice. We choose the linear combination of cosine and sine functions because we know that there will be a standing wave in the x direction. Because there are two boundaries, the wave will be reflecting back and forth. Therefore, we assume a standing wave there. Now, in the y direction, once again, we assume standing wave. In the z direction, we assume two traveling waves, one going in the positive z, one going in the negative z. Now you're going to immediately say this is exactly standing wave. Yes. So to make our life simple, we only consider plus z traveling wave. Therefore, we write h of z is a3 e to the power of minus j beta zz. This is a nice convenience. So we are now going to hypothesize that the solution fz is a product of fx g of y times h of z, which is given by this long equation here. Now we need to find out the coefficients C1 D1, C2 D2 and beta x, beta y and beta z. A3 can be anything, it doesn't matter really, by satisfying the boundary conditions. So what are the boundary conditions? Tangential electric field is 0 on the conducting surfaces. On surface 1, 2, 3, 4. On these 4 surfaces, the tangential E is 0. So we know f of fz, that is the z component of vector potential F, and we can write Ex in terms of Fz by this equation minus 1 by epsilon del Fz by del y. Substituting Fz and differentiating with respect to y, we get this equation for Ex. Ex goes to 0 on two of the walls. Ex is this component here. It is tangential component on the y equal to 0 surface and y equal to b surface. Therefore, Ex is 0 at y equal to 0. If you make Ex go to 0 at y equal to 0, sine 0 is 0. This vanishes. We are left with cosine 0 is 1. Therefore, for Ex to go to 0, D2 has to be 0. This is an important element in the solution process. What I am saying keeps repeating every time. So I am going to be stressing it now. Later on, I'll simply say that Ex equal to 0, y equal to 0 implies D2 equal to 0. It will become very easy for you to follow. Now the next one is at y equal to b, Ex has to be 0. Therefore, sine beta y must be 0 at y equal to b. Therefore, sine beta yb will be 0. This is a requirement to ensure that the tangential component is 0 at y equal to b, which implies beta yb equal to n pi, where n could be an integer 0, 1, 2, 3, any of the integers. Therefore, beta y is n pi by b. Now, the other boundary condition, which is Ey, tangential component, y-directed tangential component, should be 0 on the walls. So evaluate Ey first. by substituting fz in that equation above, 1 upon epsilon del fz by del x. Differentiating with respect to x, we get ey. This is 0 at x equal to 0 and x equal to a. When you substitute x equal to 0 in the equation for ey, we have x equal to 0, this quantity is 0, we are left with cosine 0 which is 1, therefore d1 has to be 0. And if we enforce the boundary condition at x equal to a, we want sine beta x a equal to 0 because this term is 0, this term has to become 0. This anyway is 0 because d1 is 0, and we get beta x as m pi by a, where m goes from 0, 1, 2, etc. Now we have a solution. Fz now is some unknown coefficient amn. We don't know about this amn. We'll keep it like this forever. Okay, and cos m pi by a times x, cos n pi by b times y e to the power of minus j beta zz. We have substituted those coefficients to go to 0. Basically d2 we have made 0 and d1 we have made 0. We find the equation for the vector potential z component of f. Now we are ready to evaluate the electric field and magnetic field components. This is fairly straightforward. For example, I'll just show you one, rest we'll just take it like a movie, but please do it. That's very important. You want to evaluate Ex, substitute Fz in this equation. You take the derivative of cosine n pi by b times y. It generates minus n pi by b times sine n pi by b times y. That minus sign cancels with this minus sign. Therefore, we have this equation for Ex. Ey exactly the same. We have m pi by a because we are differentiating with respect to x. It picks up a negative sign because derivative of cos is minus sign. Hx is again straightforward. Differentiating with respect to x gives me m pi by a. Differentiating with respect to z gives me beta z, and it is getting a minus j times minus j will give me a minus sign, and derivative with respect to x generates another minus sign. Therefore, hx has a positive sign. Are you following this? Hy, you can write it yourself. The last one is probably the simplest one. Double differentiation with respect to z gives me minus beta z square. Good. There is a lot of symmetry in this, and there is scope for a lot of confusion also. So if you are expected to use these equations to solve a problem, it is always nice to keep these equations handy somewhere. If you are asked to derive some equation in the exam or in the assignment for a specific condition which you have not done before, then make sure you follow these steps systematically. Please don't jump steps because they look very similar. There is very high chance for making a mistake. Now, we'll look at the concept of cutoff frequency. We know this equation, beta x square plus beta y square plus beta z square is beta square, which is omega square mu epsilon. And beta x is m pi by a, beta y is n pi by b, and therefore we have this equation. Now we ask the question, when beta z equal to 0, beta square is equal to m pi by a square plus n pi by b square, and we call this beta c square. We give a name for this, and this is known as, beta c is known as cutoff wave number. This is a very important parameter of a waveguide. So it depends on the value of a and b, the dimensions, and m and n, these are the indices representing the particular mode of the waveguide. Now, once beta c is known, which is omega c square, beta c square is omega c square mu epsilon, we can compute fc, which is known as cutoff frequency. So we have cutoff wave number beta c, we have a result for fc, the cutoff frequency. If we have two modes have the same cutoff frequency, then these modes are known as degenerate modes. Suppose if a is equal to b, then m and n will have two degenerate modes. They'll have the same cutoff frequency for, let's say, mnth mode and nmth mode, because a and b are equal, and so on. Now we talk about propagation constant. We have an equation for beta z, which is the propagation constant. in terms of Mn, Ab and beta. Beta depends on frequency and the material that is being used to fill the waveguide interior. Okay, so we know beta c square, we have shown that. Therefore, beta z square is nothing but beta square minus beta c square. If you take out beta common, you have 1 minus fc by f whole square. Square root of that times beta is beta z. So we can write beta z as beta times square root of 1 minus fc by f whole square when f is greater than fc. When f is equal to fc, beta z is 0. There is no propagation. It is cut off. When f is less than fc, beta z becomes purely imaginary. We have an option whether to choose a plus sign or a minus sign for j. If you see the equation for fz, we have e to the power of minus j beta zz. When you substitute this value of beta z corresponding to f less than fc in that equation, if you had chosen a plus sign here, this would have given me an exponential term would have had a positive quantity in the exponent, which doesn't represent a decaying wave. It's not a realistic wave. It is an amplifying wave. So if I choose a minus j minus term here, then when we substitute this in this equation here, it gives me e to the power of minus some real quantity. And therefore, that represents a realistic system. And hence, we choose minus j or a negative sign for beta z when f is less than fc. This is very important. Please remember this. Okay. Once we know beta z, we can compute the phase velocity, which is omega by beta z, and it's not very difficult to write these three components there. What is very interesting is when f is greater than fc, phase velocity is u naught upon square root of 1 minus fc by f whole square. Now, therefore, phase velocity vp will be greater than u naught because the denominator is less than 1, where u naught is omega by beta, which is 1 upon square root of mu by epsilon. This is the velocity of the wave in an intrinsic medium. Therefore, the phase velocity inside the guide will be higher than the velocity of electromagnetic wave propagating in that medium in a homogeneous intrinsic medium. So if I were to talk about light, then we can say that this phase velocity of wave inside a guide is greater than that of the velocity of that wave propagating in free space if it's filled with epsilon naught and mu naught. So this is a very interesting concept. You can have phase velocity greater than that of velocity of electromagnetic wave in free space if the guide is filled with nothing. Now you can compute the wavelength. Beta z is 2 pi by lambda g. Therefore, lambda g turns out to be greater than that of lambda. So the wavelength is longer as frequency of operation is greater than fc. When frequency of operation is equal to fc, wavelength becomes infinity. Very interesting. Now, we can talk about wave impedance also. We have the field equations Ex, Ey, Hx, Hy, and we can define for a positive z going wave impedance as Ex upon Hy, which is also equal to minus of Ey upon Hx, is omega mu by beta z. How did you get this last result? It's straightforward. Take Ex divided by Hy and cancel off all these common terms. What will be left is omega mu here upon beta z. This epsilon will cancel with that epsilon. That's straightforward. We know the equations for beta z for three different conditions. Therefore, wave impedance is given by these three possible results. F equal to Fc, the impedance is infinity, no propagation possible, nothing goes in. F greater than Fc, impedance is greater than that of eta. Eta is the intrinsic impedance of that medium that is filling the guide. But when F is less than Fc, impedance is purely imaginary, but it is inductive in nature. So in case of a TE to Z mode, when the operating frequency is less than the cutoff frequency, the wave impedance is inductive in nature. This is an interesting result. If I were to plot omega versus beta, called omega beta diagram, this yellow line represents omega beta diagram for a TEM mode, because for a TEM mode, beta is equal to omega times square root of mu by epsilon. The slope of this line will give me the speed, velocity of that wave in the intrinsic medium. But for a rectangular waveguide, we see the cyan colored trace. There is a value of there is a value of omega when beta z becomes equal to 0, and we call that omega as omega c, the cutoff frequency. Now, this is known, and if I choose any point beta z comma omega, the slope of this line which joins the origin to that point is omega by beta z, which is the phase velocity. So as we move on different points on this curve, the phase velocity changes. At cutoff point, the phase velocity is infinity. When the frequency of operation is far away from cutoff, somewhere in this region, phase velocity will be almost same as u naught. This is parallel to this yellow line here. So that is, phase velocity will be same as the intrinsic velocity of the plane wave in that medium. This is an interesting kind of a plot. We'll probably get a chance to come back to this plot sometime later as well.